Okay, we've reached the end of the reading period. So let me share the book first, and then meanwhile, think of any questions that you want to start off with or things that you want to discuss. Let's see. Let's see now. Are you seeing the book?
Yes.
Okay, thanks. Okay. Okay, so anybody want to start with a comment or question?
Yeah, I had a query with respect to OOV buckets.
Yeah.
Uh, I think so. We can tackle that when we reach that section. If you're going paragraph wise.
Okay, so sure. Just hold on to that and ask it when we get there.
Okay, cool.
Anyone else? Okay, so sort of the overview of this section is that they show you how to do pre-processing. Actually, another way, it shows you several levels of doing pre-processing. Each one of them is more sophisticated than the last. And then in the next section that we do on Sunday, there will even be a more sophisticated method that will be shown. But meanwhile, you can recognize all of this is what we're doing. The first example they start is the standardization, and you recognize that, right? You first compute the means of your training set, and you compute the standard deviations, and then you divide the mean, you map each point to, the input. You map each input point to the input minus the mean divided by the standard deviation, and that's the standard scalar method that we're used to from scikit-learn, right? And then remember there's this extra parameter EPS, which is a small number like 10 to the minus 15, and it just prevents overflow in case the standard deviation gets small. So that's the reason for introducing it. So does everybody recognize this then? It should be something familiar to you from before. You're basically mapping each point into the number of standard deviations away from the mean, right? Okay. Okay, so then he says, okay, this is one way to do it. And then a more sophisticated way is to build a class that does the same thing. And there's this, it inherits from keras.layers.capital layer, which we could go and look up. But the main thing is that it has a method called adapt, which basically grabs your data sample and calculates some stuff that it needs. And in this case, it needs the means and the standard deviations. And the advantage of this class method is that these things are hidden inside the class. They're not left floating around like they are in the in this way of doing things, right? So, and then we're using this call method, which we've seen before in FastAI, where if you haven't, what it does is it makes the class into something that as soon as you instantiate it, it executes this thing. Most of the time, if it doesn't have a call method, then the class, when you instantiate a class, it's just basically an empty container, and you actually have to give it inputs to make it real. But in this case, it's going to execute some code in the process of instantiating, a version of, well, at the same time that it creates an instantiation of the class, it actually executes some code, and that code is that it actually does this standardization calculation. Okay, and then they show how it's used. So you instantiate the class standardization, but it needs to have a sample. So you you provide the method adapt with that data sample, and then once it does that, I believe that's when it makes the calculation. Anyone, if anyone knows the object-oriented programming better, just step in if I didn't say it right.
I think so. When we call the adapt method, then the call is called with respect to the life cycle of it.
Yeah, that makes sense, but um, it's not. I mean, it, I thought that when you call the standardization, it well,
No, Joseph,
so,
the initialization and calling are still separate. They just look similar. So the first step is initialization and second is adapting. And then you would still have another step, which is standard layer. Then in parentheses, you would pass the inputs to it.
so when you write standard
Yeah,
layer equals standardization,
that's
nothing
just the
gets done yet.
initialization.
That's
No.
just the initial. Then when you say
Yep.
standard layer dot adapt to data sample, now you've given it the data, and now it can go ahead and process the call.
No,
And
that's
no.
in that step. It just
Calculates
it's
the mean and the standard
yeah,
for
it just calculates
data
the
sample.
means and standard deviation, and then there will be
Okay.
another step where standard layer parenthesis, and you would pass the inputs again.
Right.
Okay. So
Because
in
you might
this,
be passing test data or something else, right? You are not just doing it on the same data sample every time. You might
right.
be
So
passing
this,
some new data as well.
I see. So this line here just takes the sample and computes the standard deviation and sorry, it computes the let's see.
It can be, so you basically send in a data sample. So if you
Yeah.
have 10,000 rows, let's say, you're passing in only 1,000 rows, you
Right.
calculate the mean and the standard deviation for that, which is basically adapting to that data sample.
Right. And now it's a stateful
Right.
system now, and when you give it some more data, it already remembers this mean and standard deviation that it's going to use to normalize.
Right.
Okay.
So next time when you use standard layer, it's just using standard layer, since call has been defined, that will call the call function. And since you already have the mean and the standard deviation tied to it because it's a class and it's stateful, then you just subtract the standard mean and divide by standard deviation.
Good. Okay. So
Question, isn't it
let's
the
see.
case that which sample it does just for the sample, and actually when you provide the data, it recalculates the mean and the standard deviation for the entire data set?
No, I don't think so.
No. I think there's a mention of that here, right? That if you find a good enough distribution of random samples, calculating just the mean and standard deviation for that sample should work well for your whole data set.
And when you're passing in test data, you would use the
Correct.
statistics of the trained data, right? You
That's
won't
right.
recalculate
Yes.
it.
Yeah. It's not gonna.
With the
It's not gonna
training sample
recalculate.
itself, the sample has to be representative. Otherwise, it could be quite different. If you're using 1,000 of 10,000 and the 1,000 isn't representative, then you have an issue, right?
True.
Yeah.
Yes.
Yeah. Okay. So let's go back. So there's the. Okay. So here's where we are. We've let it do the adapt method. It doesn't have to be the full training set, so you just have to be sure that you've selected enough of the and randomly selected instances. In the case when you don't have a time series, you should have a random set of enough examples. And here they say a few hundred randomly selected instances, depending on your task. And once you've done that, you can use that like a normal layer. So now you have a sequential layer. You add the standard layer that you've. Okay, so this is how you would build it. I guess you would first instantiate a sequential layer, then you would add on this STD layer that you just defined. Then you would create the rest of the model, which would presumably be, layers and activation functions and all that. And then once you know that, you compile the model and you fit the model, just like in scikit-learn. So, okay. And now they say that by the time you read this, you'll have a layer that's already predefined to do this. I didn't try looking this up, but presumably it's already there. But that's okay because it's good to see. It's good to see how to build this up from scratch, like we just did. Okay. Okay. So the next thing is encoding categorical features using one-hot vectors, and you may have seen this before, you may not have. In general, when you have categories, they're not necessarily going to be ordered. So, you know, going back to the California housing data, you have location could be, you know, ocean property, inland property, near ocean property, near bay, and island. These are just different categories of housing property. There's no numerical ordering of these things, but you still need to get them into numerical form. So the solution that people use is they encode. They use one-hot encoding, which means that you would have a vector of ones and zeros. A vector of length equal to the number of categories, and there's an entry of 1 for if you want to refer to ocean category, then the position ocean should have an entry of 1, and all the other positions would have entries 0. If you want to refer to a near ocean, then the third entry should have a 1, and the rest of the entries should be 0. So that's the one-hot encoding. But so they show how that works. I guess the first step is they generate indices. In this case, 1, 2, 3, 4, 5. There's 5 indices: 0, 1, 2, 3, 4, 5. And then it knows how to one-hot encode things once you tell it what the indices are. But here they add this twist of these extra what they call buckets. In this case, they added 2 buckets, and buckets are just extra positions in this sequence of categories. They're just extra categories, if you will, and they're there because you can think of this when you look at a batch. You may not be seeing all the possible categories that are in your data set. You know, if you look at a batch of 32 housing properties. There may be some categories that aren't represented among that batch. So you reserve these extra 2 positions, these extra 2 buckets, out of vocabulary buckets, they call them, for those categories that aren't in your aren't in your batch. So so now they just go through this, go through the steps. First, define the vocabulary. That's the list of all possible categories. So in that case, our vocabulary would be ocean, inland, near bay, and island. Then you create a tensor with the corresponding indices, 0 through 4. Then you create an initializer, passing it the list of categories and their corresponding indices, like we have here. But we also, let's see. Oh, and the last, let's see. The last 2 lines, so I can't see this one. Okay, this is the first one where we create a vocabulary. Here's where we create the indices. Here's where we create we do this initializer, telling it that we want two extra buckets. And then we create a table, which we pass it the table init that we defined here with our 4 indices. But then we also pass it this number of out of vocabulary buckets so that it knows that there are 2 extra categories to initialize with. Okay, so here's how it works then. If we look up a category that doesn't exist in the vocabulary, then the lookup table computes a hash of this category and assigns the unknown category to one of the out of vocabulary buckets. So what that means is that suppose we had another category called, I don't know.
Inland desert.
Inland, I was just thinking of desert. Yeah, desert. Okay, so you could have a category of desert. You come across that in your training set and you don't, or you come across that in your next batch and you don't know what that is yet. So you just assign it a hash function, which is basically just mapping it to some number. You're just mapping it to some number, some large number. And that's what it means to hash it. And then you would assign that unknown category to one of the out of vocabulary buckets. And let's see, a hash of this category, use it to assign the, I'm not sure how this, okay, I know what a hash is. It's just mapping the category to a number, but then using it to assign the unknown category to one of the buckets. And the two extra buckets are numbered 5 and 6. So the hash would be some number that we then do something to, like take its modulo or something, and that will give it either a 5 or a 6. It's kind of like a randomized way to assign this hash, which is a large number, to one of these two extra buckets, if that's clear. Any questions about that?
So you have to have a game plan before when you build this model, of all the potential number of out of vocabulary buckets you're going to potentially have. So in this data set, we do a first pre-processing and we identify 6 buckets. So but you don't set 6 buckets, you actually set 9 or 10, leaving room that at some point you might have additional data that would have additional buckets. Does that sound right?
Yeah, except in this example, we had 5 buckets and then, sorry, 5 buckets, which were the initial classes, right? And then we reserved 2 extra buckets for unforeseen cases where where we encounter cases we haven't seen before.
Right.
But what you said is right. Yeah. Yeah. And you're right. We have to know something about how many extra buckets to have. I mean, you have to have some kind of foreknowledge to be able to say, oh, I need 2 extra buckets, or maybe I need 3, or maybe I only need 1.
So is there any rule of thumb that anyone knows how that is kind of picked?
Mm-hmm.
I mean, if you're trying to draw parallel with NLP, you basically just have one OOV, right? Not in vocabulary, you just say one word for that. But here, for categorical, it seems to be like somehow he's picking those 2. And I really don't understand, even if you have a bunch of things which is out of vocabulary, how does it help in putting them in like multiple buckets rather than just grouping them up together?
Yeah, so let's think about that. You can look at your training set, and you have this whole training set with maybe thousands of examples, and you could look at the number of unique categories and say, oh, I have 15 unique categories. And then you can say, but then I can look at individual batches of 32, and then I might find out that in each individual batch, I only see maybe 10 of the 15 categories. So there is a way to get a feel for how many extra categories you need. So that answers your first.
I know, I'd still be doing it with my whole training data, right? Why would I be looking at just a batch? If I have access to all my training data, I would look at all of this, and OOV would be something which during test time would come out of pretty much nowhere, which I wasn't expecting. Right?
Yeah, I guess that's true. So if you have access to all your training data, you know how many categories that you could initially have, right. And then you don't know anything about your test data because you're not allowed to look at it. So yeah, you have to know something about how many extra categories to expect in some way.
So let us say we do expect. You're not even actually predicting how many new categories would come in, right? Because if you look at how that hash function works, it kind of does hash mod of num OOV buckets. So that'll just give you 0 or 1 in this case because it's 2, and then you add like length of vocab to it. So that's how you end up with 5 and 6.
Yeah, so you might have 100 extra categories, but you're just mapping them into two buckets.
Right.
Yeah.
And that mapping seems random too, right? Like, or am I missing something with the hash there?
Yeah, it's random. It's random, definitely.
So then it's really not learning anything. I'm in fact just dumping it into 2 buckets there and putting it.
Yeah, so, and I'm not sure why. I mean, your first question was good because you said why not just map the unknown ones into a single bucket. I don't know why they're using 2.
Right. Actually, if you look at the last but 3rd line, in fact, he goes on to say the more unknown categories you expect to find during training, the more OV buckets you should use.
Yep. And just to add, these buckets can be a group of words or a group of sentences or a paragraph or something. So down the stream, if we have some sort of a application like document sorting or such, uh, there these buckets might come in handy with respect to the downstream task that it has to perform. Uh,
So in what way would they come in handy?
for example, if you want to sort out a list of paragraphs that have, if we talk about medicines, and you want to have an application of a particular medicine in certain context, a particular drug in certain context, then you can type in those words, and those semantic embeddings might causally search for those and list down those paragraphs as buckets to you.
Mhm.
But aren't these buckets a random, Mayank? Like,
Uh,
let's say, going back to your example of medicine itself,
mhm.
why would like two medicine names fall in one bucket and let us say the bicycle's name would fall in the other bucket? Like, I don't see how that mapping is happening if you're just taking like a mod.
Well, it is deterministic. Hashing is deterministic because every time, so if you have this unknown category like a bicycle, right, and everything else is a medicine, the bicycle is going to get mapped. Every time it sees a bicycle, it's going to do this hash function and take the mod, and it's going to end up in one of the buckets. But the next time you see a bicycle, it's going to do the same. It's going to deterministically end up in the same bucket.
Is that
Yes.
really, is that
Yes.
true?
Yes.
Because
Hashing is a one-way function, and it's deterministic.
No, that I agree, but I'm saying how would hashing know the difference between a bicycle's name versus a medicine's name? Both would
I'm
be
sorry. I'm
strings,
sorry.
right?
A bicycle cat. I was thinking of a bicycle category. I mean,
But
so if
that
you,
it doesn't know in any way, right?
yeah. So it comes across this category, this new category called bicycle, right? And so then it says, okay, I'm going to generate a hash, and then I'm going to take the mod, and then I'm going to put it into either 5 or 6. But
Right.
every time it sees that category again, it's
Correct.
going to, and so let's say it first decides, okay, I'm going to put bicycle into 5.
Right.
Then every time it sees a bicycle, it's going to
Correct.
put it
That
into
I
the
agree.
same category. Okay, so
Right.
that's how it works. So the way that I understood hashing works is that if you have a very large number of categories, and you don't want to have you don't want to have a category a one to you don't want to have a one hot encoding because that would take
Mm-hmm.
too much code. So you say, okay, I'm gonna hash these categories so that some of them are going to end up in the same bucket, but right. And so you could have, like, say you have 10,000 categories, but the way you can do the hashing, you might arrange it so that 60 of these are going to always end up in one bucket, and the next 60 of them are going to always end up in the next bucket. And so, instead of having a unique bucket for each category, you're you're mapping groups of categories to the same bucket, but always to the same bucket.
But that is random.
It's random, but every time you see one of these categories, it will always get mapped to the same bucket because of the way
Can I
hashing
just
works.
point out one thing? So in the last sentence, he says the more unknown categories you expect to find during training. So that's a really weird thing, right? Why
Oh,
would
yeah,
you
that's
find
true.
unknown
Correct. Yeah.
categories during training? And like Rakil pointed out, there is no point of having different OOE buckets. Like even one should help you. I mean, one should be sufficient, right? If you are finding out unknown categories while you are testing, it doesn't really help you if you have that many OV buckets because they're all random anyway. So it doesn't help at all.
Okay, well, let's think
So
about this. Suppose
what
you
he's
have an
thinking
example.
of
Sorry.
here is during training.
Yeah,
Sorry.
something
Yeah.
during training. Yeah, that's a good point.
But
Yeah.
yeah, there's no, I think you can just get all the categories you have in your training set and have that many buckets.
Buckets, right?
And
Yeah, but
have just one
suppose,
OV bucket
okay,
to something that you
well,
test.
but suppose you have, okay, suppose you have a language with a vocabulary of 30,000 words. And suppose you have, as your training data, you have maybe 5,000, a text of length 5,000 words. Well, you're not going to see all the possible words in
Correct.
your example, right?
Yep.
And so this is a case where you might want to, you don't want to just map new words all into one bucket, because you want to be able to learn something about these words. So you want to map different words into different buckets. So you want to have maybe an extra couple of hundred buckets.
But that's
Won't
not what
learn
we do,
anything
right?
anyway, right?
Yeah, exactly.
Pardon?
If it's an embedding layer, yes, I agree with you, because you're going to learn something. It makes sense to map it to every word to something new. But otherwise, when you do OOV, even in NLP, everything which is not there in the vocab just gets mapped to one thing, right? One unknown.
Yeah.
It's not like multiple unknowns are there in that case.
Yeah.
The very next section where he talks about the embedding layer, there I agree with what you're saying. Like, yeah, you map it to a new thing, it'll learn. There is something that you will, at the end of the training, that you will end up learning new.
Yep. Take an online example. Suppose you have a new product. If I take Amazon, for example, and I construct a scenario with respect to adding new products, and if that particular product falls into a category, that then that can be grouped causally into that category based on the meta tags that were defined previously, and that bucket can be assigned to that whole group while training for the recommender system, if we are building that.
What's meta tags?
Meta tags will be kind of a key value pair in which suppose if we take Amazon, for example, then each product must belong to certain ID or which
a certain category, let's say like medicine or shopping or like home decor or something like that. I agree with you, Mike, but the thing that kind of breaks down in your explanation is the category, let us say, is home decor, medicine, bikes. He's taking a hash of that, right? The moment you take a hash of that, then it becomes random, right? If you were mapping the meta tags by itself, then I agree with you. Then all the meta tags will be kind of grouped together in each bucket. I don't understand this whole business of hash.
But hash is deterministic, buckets. Right?
Yeah, it's deterministic. That is true. But see, for example, here, he did hash of desert modulo number of buckets plus length of vocab, which gave us 5, right? Now, I tried changing that desert to like different things, and I still always ended up with 5. I never could get 6. So I don't understand. Whichever word I put till now in there, irrespective of whether it's connected to a desert or not connected to a desert, it still gets mapped to 5. Does that make sense?
I think, yeah, but I can understand Mayank's example. Like if you're doing some kind of online training, then suppose you come across a new category, and you can still train with that new category, because that particular new category always gets assigned to the same OOV bucket. Suppose you have like 3-4 buckets, the new category that you come across will always be assigned to say bucket number 2, and then while training you can end up actually getting a good embedding for that new category that we just came across.
So doesn't that mean for every new thing that you find, you potentially should just create a new bucket, because down the line you could learn?
Well, but the I guess hashing is designed for the situation where you have so many, overwhelmingly many categories, and it would slow down. You don't have enough compute to keep track of them all. So what you end up doing is grouping some of the categories into the same bucket. So in other words, if there's 10,000 categories, you might decide to create only 100 buckets by mapping your hash into modulo 100 or something, right? That way you could map any number of categories. Any number of new categories can be mapped into 100 or 60 or 200, whatever number you decide, because you get to control that modulo number, right? that controls the number of hash buckets, right? So if you say modulo 100, that means you're allowing only 100 hash buckets, only 100 buckets, right? So whatever comes in has to be mapped into one of those buckets.
Yep, and this modulo will depend upon the your throughput, the various constraints your hardware has with respect to memory, and how many batches of data it can concurrently take in, and then pre-process it and hash it to those hash values. So this will all depend upon that, and for each and every, if we take that online example, that modulo those hyperparameter, as you just said, 100, that can be scaled up or down based upon.
Yeah, it's like a hyperparameter, and I think that there must be like a rule of thumb. Like, in other words, if I want 10,000 categories, if I start with 10,000 categories, like what's a reasonable number of buckets to sort them into? We can maybe look that up or see. There must be some kind of a rule of thumb.
So once again, so this is what would happen, right? So if you go back to our categories, we would have one ID for near bay, one for island, one for, I don't know, less than 1 hour to ocean. Those 5 would be fixed, right? Now, let us say you come across desert, you'll come across, I don't know, mountain. All those are going to get mapped. More than one thing is going to get mapped to one of those buckets.
Yeah.
Randomly.
Yeah.
And there's going to be a bunch of other things which will get mapped randomly to this other bucket number 6.
Yes. Right? But those groups that get mapped into one or the other of the buckets, they'll always get mapped into
that is
the
fine.
same bucket.
I'm saying, I'm talking of the mixing within the bucket.
Yeah.
There is going to be inherent mixing within the bucket.
Yep.
Okay.
Yep. So in other words, you're not going to be able to learn as fine-grained as you want to, but you'll still be able to learn something, even if you have to group a bunch of categories together, if that makes sense. Yeah.
But it's always best to look at your entire training set and create one bucket for each, right? That's always the best thing to do.
Well, it depends. I mean, if your training set has 10,000 categories in it, and you don't have enough compute to handle, to be able to train a model like that, then you have to start thinking about bucketizing.
Or probably at the next section of embeddings.
I mean, even in embeddings, you're still having separate I mean, each category is separate. They're not bucketed together.
That's right. So I guess the next section, when they talk about embeddings, you can have a large number of categories that and handle it, because you're using, instead of one hot encoded, you're using continuous vectors. Yeah. Yep. So then you still have this hyper. Yeah, and you still have, that's right, you're still keeping them separate. And here you have the hyperparameter of how many, what dimension is the vector, what dimensionality should the vector be to handle X number of categories. And again, I don't have a good feeling for it, but there must be like a rule of thumb.
Yeah, there's a fast rule of thumb, right? Their tabular section kind of deals with, they cap it off at like 600. So if you have more than 600 categories, it'll be mapped to 600. Otherwise, they do something like, I think, 1.6 times number of categories. Oh, there's a formula, basically, some rule of thumb.
A heuristic formula, yeah. I remember where I came across this once, and I was looking at this Kaggle competition, and I can't remember the name of it now. But it was a situation where you had, a huge number of categories, and you were doing online learning. You couldn't fit the whole model into memory. And so, just as Mayank was saying, it was an online learning example, and that's where you had to use this discrete bucketization rather than the vector encoding that we're going to look at next. But right now, I can't clearly say why one should be preferred over the other. It's always better to be able to map every category exactly to a new, to a vector. It seems to me that's a better way to do it. I'm not sure why you would have to use the hashing trick and the buckets and all that. So we can keep that in mind, and if anyone comes up with an explanation, you can post it on Slack. Okay. Okay, so I guess we've progressed. We can look at encoding categorical features using embeddings. And this we've seen maybe before if we've taken the NLP class, or if we've taken even in the FastAI, they've talked about word2vec, which is basically that. It's taking words as categories. You have this 30,000 word vocabulary, and each word is considered a new category. And then you can one-hot encode the words, but you map them to vectors, and that's what this word2vec thing is, invented by some Google engineers in 2013, where each word gets mapped into something like a 300-dimensional vector. So he talks about the reference. Let's see, where does he talk about that? Yeah, this paper, this word2vec paper, and you learn. You start out by say you decide you're going to have 300-dimensional vector embeddings. You start out by randomly initializing them, and then you learn the embeddings with a neural network. And then so every word gets mapped to a 300-dimensional vector. And then you find out some things that there are interesting properties of these vectors, like words that are synonyms tend to be near each other in that vector space. And then the surprising thing that was demonstrated in this paper is that it understands analogies. You remember the SAT questions where you have, treasure is to gold as, I don't know, I don't know a good analogy, but you know these analogies, right?
The head is pants are to something.
Pardon? Say what?
Hat is to head as pants are to.
Yeah, that's a good one. So these are word analogies, and it turns out that these word embeddings understand in some way. They encode these analogies, and the famous example is the king minus man plus woman. If you take the vectors for king and subtract the vector for man and add the vector for woman, then you get the vector for queen, or very close to the embedding of the word queen. So it understands these analogies. And then another one, they say, if you say Madrid minus Spain plus France, and that gives you a word whose embedding is close to Paris, right? Because Madrid is to Spain as Paris is to France, them both being capitals, right?
I have a question. So is this graphs? Is this graph relationships?
It's not the same as graphical neural networks, but it's a two-dimensional. Well, you can visualize it in 2 dimensions, and that's what they're doing here. You look at this, what they call the embedding space. Let's say you're trying to embed these categories into a 2-dimensional vector. So the y direction will be one of those vectors, one of those dimensions, and the x direction will be another one. And then every vector, every category is encoded as a 2-dimensional vector, which means it lies somewhere in this space. And let's see, what's the point they're trying to make here? Let's see.
Randomly initialized, and you see them move. That's the gray.
Right. The light blue are the randomly initialized ones, and then the water-related ones start moving closer together, and the land-related ones also conglomerate into one area of the space. And that's what happens with the words, except it's much more complicated because they're higher dimensional, right? You can't visualize a 300-dimensional vector, but that's the idea. Okay, well, and here's that analogy shown. So here you try to shrink the 300 dimensions into 2 dimensions, and so this is sort of a schematic of what what they're saying, that you know, here are the embeddings for king and queen, and they're sort of directionally related to each other in the same way as the embeddings for man and woman are related to each other. So, you know, king is this vector that goes from here to here. Man is the vector that goes from here to here. And the difference of those two vectors is a vector that goes this way. If you remember if you sort of have to remember back to your Cartesian geometry class. Here's the vector for king. It points from the origin to king. The vector for man points from the origin to man, so it's this vector. And then king minus man is the vector that goes from man to king, all right? And the same thing with queen, that's that vector. And woman is the vector that goes from the origin to there. And queen minus woman is the vector that goes from there to there. But what they're saying is that that this vector, man minus king, is very nearly the same as sorry, king minus man, that's what I said here, is very close to, well, I guess that they're writing it this way. If king minus man is to be the same as queen minus woman, then you would expect king minus man plus woman to equal queen. And when they do that, they find that it's very close to queen. Okay, it's not exactly equal to, but it's very close to. So that's what they showed in that Mikolov paper on Word2Vec. And then, of course, they go into this bias thing that you can find that in the English language, a lot of times, you know, there's gender-specific roles, like men are supposed to be doctors and astronauts, and women are supposed to be nurses and teachers and that kind of stuff. So you can uncover a bias in your vocabulary. Let's see. Okay. Okay, so then he goes through the mechanics of creating an embedding. You decide what the embedding dimension is going to be. Then you give it the initial. Then you give it this. You initialize your embedding by giving it the length of the vocabulary plus these extra out of vocabulary buckets. And oh, well, now here, okay, length of the okay. So now that means you're encoding this number of categories, the length of your vocabulary plus the extra 2 buckets. So you're encoding those 6 categories into a 2-dimensional vector. That's what this thing is telling you. And this is the initialization. Then embedding matrix is converted into a tensor like that. Let's see. Okay, so the embedding matrix is a random 6x2 matrix. Why is it 6x2? Oh, because it's 6 categories. That is the 4 categories. I thought there were 5 categories in the vocabulary. So now I'm a little confused. I would have thought it would be 7x2. And the 2 is the embedding dimension. The embedding dimension is 2. So 5, 6. So anybody have an insight as to why this isn't 7?
Yeah,
because we had
it should be 7. Yeah.
Yeah. So 7x2 matrix, and it's stored in a variable so that it can be tweaked by gradient descent during training. So we can look at the embedding matrix after we create it, and we see it should be 7, but it's 6. But the point is that it's randomly initialized right now. Oops, sorry. Okay, now we use these embeddings. 1, 2, 3, 4. Oh, I guess he's using, oh, sorry. Why is this 1, 2, 3, 4?
That was an example.
That's just the input, yeah.
Yeah.
Just an example. Okay, just an example of of 4 data points?
That he's going to use the embedding matrix now with
Okay.
this for data.
Okay. So first you look up the categories to get their indices. And then there it is. I guess we had already defined near bay to be 3, desert to be 5, inland is 1, and that occurs twice. So, and then lookup. So now we do embedding lookup, giving it the embedding matrix, which is the 6x2 thing, and the indices, and then it's able to look up in the embedding matrix and find the vectors that we need, the embedding vector. Sorry, the two-dimensional embedding vectors, and there they are. So these are the embedding vectors for what was it? Inland, which are the same as they should be, and then this was I forget what the other two categories were. Desert was the third from the last, and near bay was the first. So near bay is this one, desert is this one. And remember, we haven't trained these things yet. These are just the randomized initial values. Okay. So now he shows another way to do this, I guess. You use this embedding layer that can handle an embedding matrix. Input dimension is the length of the vocabulary plus the number of buckets. So in this case, the input dimension would have to be 7, right? Because we had 5 words and we had 2 extra buckets. And the output dimension is the embedding dimension, which is 2. So so now we can call this and give it the input that we had defined before. And then it gives us this array. Again, the last 2 are the same because they should be. But I'm not sure why. Okay, I guess these are just not these are just different initial values. But I'm not sure why these are all small while these are all large, because we still haven't done any training yet. Putting everything together, we now create a Keras model that can process categorical features with regular numerical features and learn embedding for each category as well as bucket. So in this case, we're considering a more general kind of problem where we have numerical features. I think he's doing that. Numerical features plus categories. So this is a more general kind of problem which you might run into where you have data that has some of the features are categorical and some of them are numerical. So that's good that we're now getting to that more kind of general problem. So the regular inputs are the numerical inputs in this case, and the categories are the categorical ones. So we do this as before. We get the indices for our categories, and then we get the embedding for our category we get the embedding for our categories by giving it the output dimension. Again, here this should be 7, I believe. But let's just pretend that it's 6, which would mean that there are 4 words plus 2. There are 4 categories plus 2 out of vocabulary categories. Okay, so then that's our cat embed. Then our encoded inputs are, we concatenate together the regular inputs and the embedded and the categorical embeddings. So this is basically, now it looks just like an ordinary numerical input with this x with 8 plus 2 dimensions, right? 8 dimensions for the regular inputs and 2 dimensions for the embedding. So now we have a vector of length 10. And then the output layer is a dense layer that maps to one number. So now having defined the inputs and the outputs, we can define the model. And something isn't clear to me, because I think this inputs should be not regular inputs categories. It should be the encoded inputs that we gave it. that we, because otherwise, what's the point of doing this? Here's where we combine everything, all of the categories to make, here's where we combine all the inputs, concatenate them all together to make a vector, a 10-dimensional vector. And that should be the, to me, that should be the input here rather than this thing. So does anybody have any comment about that?
If you do that, then the embedding matrix is not within the graph. So then there's no backprop going to happen and nothing is going to train in your embedding layers. So you want to start all the way from your regular inputs, have that get mapped. So you can draw the full chain through the embedding matrix and then through the dense layer and then get your output. That's what my understanding is.
But here the input to any neural network model, you would agree, has to be numerical, right?
Right. So that's going to draw the chain, right? So you're passing it regular inputs and categories. It's going to fill in that in-between stuff, which we just wrote about this.
You're saying that the model knows how to do that.
Yes.
The keras.
Yes. So when you do, I think when you do keras.models.model, you just need to specify what your input is and what your output is for that line of code. And about that, you would have already defined how you reach from your input to your output.
Okay,
so that's why internally, it can draw that chain. Yeah.
So internally it knows how to do that. But
init and then the forward of PyTorch or whatever. So yeah, I agree with what Raquel is saying, which is the reason it is the categories is because you have to take it through the embedding layer, and the reason you need to do that is otherwise your embedding layer won't train.
yeah, but
So you define the network and then you pass in the input to the network, and the network in this case includes the embedding layer. So you have to give it the input before the embedding layer, which is the regular inputs and the categories that you pass into the cat embed.
Okay.
To the cat indices and then the cat embed.
Okay, that makes sense. But what doesn't make sense is why bother to define this then?
So if you look at what is getting passed into that, is you're using that concat layer and you're combining regular inputs and the cat embeds, right? So that's what we got. Regular inputs is straightforward stuff. Cat embed is the encoding. You're passing that encoded inputs, which is the concatenated stuff, to the dense block. That's what is happening in the next line. So if you basically just keep substituting one line into the other, you'll see that the full chain is forming.
Oh, I see. It's got this.
Yes.
That's where this is used. Okay,
right.
I see. Okay, thank you. Okay. Okay, now I guess that makes sense.
Yeah, same thing. If you look at cat embed, you can fill it from the previous line, and then everything just forms the chain by that.
So this is so you can calculate the back propagation. Okay. So we see it takes two inputs: a regular input containing 8 numerical features, a categorical input containing 1 categorical feature per instance, which in this case is, I guess, 6. Layer to look up the index, look up the embedding, concatenate the embeddings and the regular. Yeah, we've seen that. And in this case, they add only a dense layer after that. So then he says that there's this method called text vectorization, which I guess it wasn't available at the time that he wrote this, but maybe now it's available, which has an adapt method that you can use to make it extract the vocabulary from a data sample and create the lookup table. Okay. And then okay, then they say one hot encoding followed by a dense layer with no activation function, no biases is equivalent to an embedding layer. I guess that makes sense. However, the embedding layer uses way fewer computations. The dense layer's weight matrix plays the role of the embedding matrix.
I think the paragraph is just a long-winded way of saying you index into an embedding layer to get the embedding, and it's equivalent to multiplying by a matrix.
Yeah, and we already know that you never want to do that indexing is way faster than indexing
Exactly.
into the embedding matrix is way faster than doing the
Yeah.
the multiplication of the one hot encodings.
Yeah, Jeremy explains it much easier and much
Yeah.
shorter than this.
Yeah. So, but that's the idea. Yeah. Okay. Then the last section is this Keras pre-processing layers, which is even a more sophisticated way of doing this. This is the stuff that you know that Srinivas has been going through in the FastAI version 2 library. All this stuff, the way the FastAI version 2 implements it, right? So I guess that's what will that it's sort of along a parallel line to what Srinivas has been going over in his FastAI version 2 library lessons. Let's see. So, and so at this time he's writing, at the time of writing, I guess that this Keras preprocessing layers hasn't been finished yet, and now it's supposedly, supposedly it is. I looked up some of these things. I didn't actually find a layer of this name. They had a batch normalization. Anyway, so I probably need to look a little bit more to see.
I think they're all still in the experimental section. It's not yet moved out.
Okay. Yeah, I did see some things in the experimental section. Yeah. So I guess it's still not quite done yet.
But they do have, like you said, Joseph, they have batch norm, layer norm, weight norm that you can just call as the specific keras.layers.batch norm, and then keras.layers.layer norm, and you can just use them.
Yeah. I guess we can look up how they're defined, and then you can figure out how they get used. This is an interesting discussion here where he says they're going to include this discretization layer that chops continuous data into different bins and encodes each bin as a one-hot vector. I guess in some cases, if it's advantageous to bin up your data instead of using a continuous variable to chop it up into bins and make it into a discrete variable. It'd be nice to see an explicit example of that, but he mentions that when you do that, of course, you lose a lot of information because you're going from a continuous variable to a discrete variable. It's kind of like the opposite direction of what we're doing when we encode categories into a continuous vector. This is kind of like the opposite, where you encode a continuous vector into a discrete number of categories. He says it loses a lot of information, but in some cases it can help the model detect patterns that would otherwise not be obvious when just looking at the continuous values. So it would be nice to see an example where that is borne out, but so I don't have intuition for that right now. If anybody has a comment, that would be great. And he points out that if you do this, it's not going to be, this discretization layer will not be differentiable because it's discrete. And so it should only be used at the start of your model. Pre-processing layers will be frozen during training, so their parameters will not be trainable. Their parameters will not be affected by gradient descent. So that's the thing to remember about the pre-processing steps, is that they're not, you don't want them to include any trainable parameters. And that's what he says here. You should not use an embedding layer directly in a custom pre-processing layer if you want it to be trainable. Instead, you should add it separately afterwards. So I guess the thing to remember is to separate your pre-processing steps from your training steps in your model. Okay, chaining multiple pre-processing layers using pre-processing stage class. I guess we've seen stuff like this in earlier examples with scikit-learn in this course, where you put together a list of pre-processing steps and they process them in that order. So here they define a normalization step and a discretization step, which remember is binning up a continuous variable into a discrete values. And so then you construct a pipeline that has a list of pre-processing steps, first normalization, then discretization. And then there's an adapt method that you give it the data sample and then it calculates the parameters that it needs to initialize itself. And this is kind of like what we saw before with the normalization step. Text vectorization layer will also have an option to output word count vectors instead of word indices. And so you've seen this before if you've seen the FastAI class or the FastAI Code First Introduction to NLP, where they talk about the bag of words method, where you translate a statement, a text string, into, instead of encoding each word, all you do is count up the number of, it's kind of like one hot encoding, but instead of having a 1 in each position, you have the number of times that word got used in your example. So so here they give an example. If the vocabulary contains 3 words and basketball and more, then the text string more and more will be mapped to the vector 1, 0, 2, and that's because it has 1 instance of the word and, which is your first index, 0 instances of the word basketball, and 2 instances of the word more. So if these are the indices for the vocabulary words, then the numbers that appear are the counts of the vocabulary words, and that's the bag of words method. When you do that, you lose all information about the ordering of the words. But so this is kind of like pre-transformers, but it's still pretty powerful. The bag of words encoding is still pretty powerful. Okay. Oh, and because in any text string, when you have certain words like and, the, of, words that are very commonly used, they're going to have very high counts in a given paragraph or whatever. And so, but you don't want to pay attention. You don't want to pay too much attention to those words because they don't have much information in them, right? The articles like and, the, and so on. And so you normalize things by a technique called term frequency times inverse document frequency. And what that is just you divide these occurrence numbers by the logarithm of the occurrence of that word in the whole corpus. So in the example, he says, suppose that the words and basketball and more appear respectively in 200, 10, and 100 instances in the whole training set. That's what I mean by corpus. And here it makes sense. And occurs very frequently, basketball less frequently, and more is a word you'd expect to occur more frequently than basketball. And so you normalize by the logarithms by dividing these occurrence numbers here by the logarithms of the occurrence of that word in the whole corpus, in the whole training set. So the thing to multiply this vector by would be 1 over log 200, 1 over log 10, and 2 over log 100. Sorry, and I'm sorry, the multiplication is already done. You're basically taking this vector, multiplying it by 1 over log, the first element by 1 over log 200, the second element by 1 over log 10, and the third element by 1 over log 100. That's what this inverse document frequency means. It's kind of a misnomer because it's not really 1 over the document frequency, it's 1 over the logarithm of the document frequency. But it's kind of set in stone because that's the historical name for it. So whenever you see TF-IDF, that's what that means.
Joseph, it's number of occurrences by, right? It's not always 1 by.
Yeah, in other words, you're multiplying this vector, which is the number of occurrences, by the vector, which is the 1 over the log of each number, right? Yeah. And so Right, and so as you said, it's basically the what would you call it, the Hadamard product of this with the inverse log frequency, and then the result is this vector, right? So each occurrence number you multiply by 1 over the log of its occurrence in the whole corpus. So that's why you get...
It's 1 over the documents in which that word appears.
1 over the log of the number
Correct.
of appearances in that document. Yeah, in that training.
Not the number of appearances, right? So and can exist twice in the first document and cannot exist in the second document.
No, it's the whole training set. It's the whole whatever you're using as your training set. So it's the number
word count by the log of the total number of training instances in which the word appears.
Yeah.
So that is the documents that it appears in, not the total number of times that the words appear, right?
Oh, okay. Let's see. The total number of training instances. Okay, so a training instance is a text string, right?
That's why it's inverse document frequency, right? It's the document in which it appears. If it appears there, then you count the document. If the word doesn't appear in the document, then you don't count that document. It's not irrespective of how many times the word occurs in the document.
I see. That's right. That's right. Right. So the document is the set of text strings in your training set, and either the word occurs in that text string or it doesn't, and you add all the times that it. So if you're looking for and, you look for the number of times and occurs in all the text strings. And as you said, Rekul, if and occurs twice in one of the text strings, you only count it as once, because it's just the number of, it's just either 0 or 1. It either occurs in that text string or it doesn't. And if it occurs more than one time, then it's the same as if it occurs once. That's the point you were making, right?
Yep.
Okay, so now we know how to calculate this TF-IDF. And he's saying that the text vectorization layer that's supposed to be in this API is gonna likely have an option to perform TF-IDF. Okay. If the standard preprocessing layers are insufficient, you will still have the option to create your own custom preprocessing layer, like we did before. Create a subclass of the keras layers.preprocessing layer class, I guess. And then you have to give it an adapt method, and you have to give it a data sample. And I'm not sure about this reset state argument. If true, then the adapt method should reset any existing state. So in other words, if we were doing standardization, it would reset, it would start all over again when you give it a new data set and calculate the mean and standard deviation all over again. Or if you set to be false, then it would try to update the existing state. I'm not sure what that means. Does that mean that it would add together with what it's seen before? I mean, it would combine that new data set with what it's seen before and calculate the mean and standard deviation over that concatenated data set? Is that what that would mean?
Yeah, I think like the online case.
Yeah.
You don't want to, yeah. So I think
you want to accumulate the vocabulary as you go, and it wouldn't make sense. It would make more sense to do it that way, right? Because then you have a more meaningful standard deviation and mean. And I guess there would be methods where you would maybe want to do some kind of an exponentially weighted average, like the latest batches contribute more than batches that were taken a long time ago, something like that. That could be something they've implemented too. So that's where we ended up. And then the next time we'll do the last couple of sections, and we'll probably have some leftover time because there's only 2 more sections, and maybe we can then look at the notebook and make sure that we understand that.
Just to be sure, I had a query with respect to the implementation of this in the notebook notebook. I was looking at it and I didn't find everything that's mentioned in the ending sections that we have just discussed.
Yeah, a lot of it is not mentioned, right?
Is
Something
that right?
completely
Okay.
different is there about
Yeah.
images
Okay.
and stuff. So we need a session for that itself, I guess.
Yeah. Okay, so
Because
here's
in
what we
the
did. Here's the TF record format, and then protocol. We did this protocol buffers, blah blah blah.
You just missed that one. Putting images in TF records.
Yeah, and that's not even included, right?
We just kind of saw that he said, oh, there is an IO decode and there's an IO encode JPEG, but there's some examples here. I think it's worthwhile looking.
Yeah, so next time it probably won't take us too much time to dispose of the last two sections, and then we can go back and spend most of the time on this notebook.
Yep.
Yeah.
Just to add, in the end, they have used those text vectorizations, those new classes that we talked about earlier. So I think things what the author of this notebook is trying to do is dispose of the old ways and take in the new. Maybe.
Yeah, he's anticipating the new, the new changes that he knows are coming, but haven't come yet. So, yeah. So maybe we can explore those a little bit next time too. These new pieces which are still experimental.
Yeah, these are with respect to the IMDb dataset. So that will be interesting too, because that's the use case. One of the interesting use cases on which we can implement it. So
sure. Yeah. Yeah. Okay. Okay. Great. If there are there any other questions, comments? All right. Well.